Hello. Welcome back. I hope you enjoyed the lectures from Paul on reinforcement learning and also on VAE. These are advanced topics, but I think they're very important in the new trends of multimodal. So today we are talking about fusion, co-learning, and new trends also. I will tell you more about what I mean by new trends. What we have a few administrative things, just to be sure we're all on the same page. A reminder that, as usual, the Piazza, that's the place to get the to get the live questions at the end of the class. We'll go there and answer any remaining questions that the TA didn't answer. We're past halfway. We're in week number 10. This is a pivotal moment in the class. This is the moment where we almost, after this lecture, that will be the case, almost address all of the core elements of multimodal machine learning. And after that, we're having fun. We're taking advantage of all this knowledge and look at the most recent papers on multimodal machine learning. So this is kind of a nice moment. And that's why also the last few lectures of this will be a guest lecture, because I specifically selected them to be of the state of the art or some example of state of the art in multimodal, or also in the last case, bias and fairness, which is very important for the topic of AI in general and multimodal. Just a small reminder. So next week, there's no lectures. There are no lecture on week 11. Instead, we'll do office hours. I already sent an email with a Calendly that allows you to sign up for those meeting time slots. So I invite you to sign up. Usually it's one time slot per team. I give more details in a minute about this, but and I also moved them on Tuesday instead of Tuesday and Thursday, because Tuesday was a lot more popular. And we use the Calendly so that you don't, at least you know when you will be approximately. I will do my best to keep the schedule. This not this Friday, the next Friday is already the presentation. The midterm presentations are already coming, and then the Sunday after that. For the Friday, you submit, like the same as the first assignment, we submit your slides on Gradescope and the video on Box. On Sunday, you submit your report, and then we'll have the student feedback. We will use your suggestion. Most of you suggested their preferences for topics, so we'll use that in the matching and share that with you probably around Sunday the 15th. Share that. Oh, there's a small typo. It's Sunday the 28th. Sunday the 28th is when the feedback. No reading assignment on the 11th. We're restarting the reading assignment on the 12th. And in fact, there are only, there's this week, and then there are 2 more reading assignments only. We're not doing reading assignment on week 11. There's no reading assignment on week 13, and no reading assignment on week 15. We try to keep it at a smaller number because that way you can focus on your project. So next week, if you want to get a meeting, I think there's still quite a few spots, although they've been filling out quite quickly for meeting with me. Usually the meetings will be 10-ish minutes, and we'll, if needed, we'll add a few more if there's a need for. But please try to sign up if possible before the weekend. So we'll use the same Zoom link. So it's the exact same Zoom as the main lecture, but we will turn on the activation. I want to also talk about one thing before we start the lecture, is that you are right now probably focusing on your midterm project. And we and the TAs are really there to support. You should meet with them as often as you want. But I also want to emphasize these are team efforts. And if for some reason one or more of your teammates, maybe there is a reason of they're looking for, they have job interviews or something, but there is an unbalance in the way the project is going on, and some teammates are taking on more than others. This is the right time to talk with us. This is the time you contact the TAs directly, or myself also with the Piazza. But a lot of time these issues are things we can discuss with other students and be sure that all teammates are on the same page. But please don't wait too long. Like if you have such situation, or sometimes it's just a misunderstanding of what the tasks are, or a different way of approaching work, but still don't wait that it's too far. When it's still like 2 weeks before the deadline, there's still time to adjusting. When it's a day or two before the deadline, things get stressful. That's not the time to do. Also, we sent an email about new coupons for the GPUs. If you would like to get more coupons, you can contact us. We I think send it for AWS, but we can also give more coupon for Google Cloud Platform. So please contact us. It takes a few days sometimes to get the coupons, so don't wait again on Saturday night to ask for more coupons because you need them for your report. That will not happen, but 2 or 3 days at least for that should be, in most cases, sufficient. Great. Today we're talking about fusion, co-learning, and we're also approaching new trends. Today we'll do a first quick recap on multimodal fusion, looking at what we studied in lectures 7.2, 8.1, and this lecture now complements that by looking first at model-free fusion, place where you may almost see it as unimodal model being pre-trained beforehand, and a late kind of fusion. So we're going to look at those model-free fusion, and then we'll look at the concept of local fusion and kernel function. I think this is very interesting. We'll look at it also because they can make us maybe understand the models like transformers in a different way, through a different lens, and also give an example of how kernels could be used as a multimodal approach. Then we'll talk about co-learning. Co-learning is probably the one where there is the least prior work, but probably the most future work. So for that reason, we're talking about 2 categories. We call them parallel and non-parallel. Another way to call them is strongly paired and weakly paired data for co-learning. And this week is very fun for us and hopefully for you too, because we're starting the new trends. New trends is we've been spending the last 3 weeks, TAs and instructors working together to identify new papers in the last year that are in multimodal, and try to bring them into different trends that are happening in multimodal. This is not meant as being exhaustive of all the trends, but they are some of the main trends we identified. And 2 of them we'll talk today, and we'll talk about another 7 of these trends in the lecture on Thursday. 2 of them are few-shot learning and weakly supervised. Both of them are very related to co-learning, specifically few-shot learning, and talk about the idea of the intersection of multimodal and multilingual with the goal of grounding. So this is the focus for this lecture today. So a quick recap on multimodal fusion. If you remember, fusion is this process of joining information of 2 or more modality to perform some local prediction. And so the example of that was audio and visual speech recognition. Could be seen that way, although you could also see it as a translation. One that is clearly a fusion task is audio-visual emotion. You hear my voice, you see my facial expression, you infer from it some extra higher level construct or information label like emotion. You could be identifying like an identity of someone from their gait and from their voice. You could also be answering question as well, although this could also be, it has a fusion component, but also has translation component. If you remember, about 2 weeks, a little bit ago, 2 weeks ago, we said like fusion and representation learning are not like completely different. I mean, there's really a progression between the two, specifically when we look at neural architectures. You have representation learning, but at the end, when you do that final prediction, that's usually where we start calling it fusion. And fusion makes a lot, that terms is a lot clearer, there's the difference between representation and fusion is clearer. Maybe when you look at the cases where you want to integrate domain knowledge in that later stage, you want to include knowledge. Maybe you include knowledge because one label you're looking at, in fact, could be seen as having sub-construct or some part to it, or maybe because there's a structure between your output labels. And so we talked over 2 lectures about the graphical models as one version of these where you can integrate knowledge. You can integrate knowledge maybe because you have some information about the temporal aspect of it, or also maybe because you have information about how modality work together. So maybe you know that there's something intra to that modality, like language has its own structure to it, like grammar. But there's also some different modalities could happen between modalities. You may have some knowledge on how they should link to each other. This is an example here, was from latent dynamic conditional random field. No, sorry, this one is hidden conditional random field. But the lecture today, we will focus on model-free fusion because we talk about neural approaches, we talk about graphical models. We didn't talk about model-free fusion with the like old school fusion of early and late fusion. I think it would be impossible to have a class on multimodal machine learning and not at least have a little bit on early and late fusion. But I want to emphasize also these new wave of work on model-free fusion, which we'll talk in a second. And after that, I will also talk about kernel-based method for local fusion. I will call this more of a local fusion for kernel method. But let's start with model-free fusion. I will not say back, let's say it. Back in my days, 20 years ago, when I was a PhD student, they modeled the fusion. There were really 2 big wave paradigms for fusion and for multimodal in general, was early fusion and late fusion. And it's very interesting to at least look at those 2 extremes. I think now these days we're a lot more in the intermediate fusion, what we'll call intermediate, but late and early fusion are kind of an extreme. And so early fusion, which in this case, the idea is that you concatenate early on your features. You're simply concatenating your features and then allowing your classifier to do the fusion. All the work is in your classifier. You could almost see a parallel here with joint representation, but it's joint representation when the joining is done at the earlier stage, like almost the raw data. The raw input features are joined at that stage. And then the classifier goes on and do maybe some, if it's a neural network, do some representation learning, and then eventually does a classification. The same thing could be with a regression. This is not specific to a classifier. One of the advantage of the early fusion is that it's easy to implement and also easy to implement. It's the same classifier. So whichever machine learning classifier or regressor that existed in, or maybe you go in statistics, linear regression, anything that already existed before multimodal AI started being studied even more, then you can simply use it. It's a black box in a sense. So you could, if you at least can use it in that way, if you want, you concatenate the features, and then if it's a prediction task like classification, then you label. The goal or the hope is that internally it's going to exploit the multiple feature, that it will learn the interaction. One of the challenges, these could be high dimensional, and so the classifier has to do all this. And it can be more difficult to use if features have different granularity. This is specifically true if you have language and visual. Maybe now these days you can put and have a word embedding that's both a vector. That was not true back then, 20 years ago at least. A lot of the language was done in a symbol level. So that's early fusion. It's in contrast with late fusion. The late fusion is interesting because there, each classifier is trained independently. In fact, what I didn't show here is that, in fact, there it's trained with the label in mind. It's the same label here at the end of the day that you want to predict, but you're going to train. And in the world of neural network, you could call late fusion just pre-training, but it will be a pre-training, a supervised pre-training. It's supervised pre-training, so it's the same task. It's the same task that you want to train. You pre-train, but you kind of pre-train each classifier, each modality with a classifier, and then you will have a fusion mechanism. And that's where it gets really interesting. And today we'll go through many of these different mechanisms. So I have a unimodal. It could be an SVM or an LSTM or a transformer if you want to make it even more complex. But you train each unimodal, and then you will, once it's trained, and it's not just pre-trained in the sense of unsupervised pre-trained, it's pre-trained for that exact same task. So it did everything it could, as good as it could, in that unimodal, and then the fusion mechanism is going to go on top without any fine-tuning of these classifier. You're just not changing anything. You're just going to say, this is the best I get from each of these, and let me see how to fuse that information. And so it is useful, this kind of approach, because then each of them can be trained with its own data. It could be, let's say, that label you have here. Maybe you have it on many data sets, but on some data set there was only language available. Let's say you look at emotion or sentiment. Many data sets for sentiment have only language and don't have multimodal. So the language classifier could be trained on a lot more data maybe than audio and visual, or maybe on visual you have more information because you have those image base, and you could, so that allows you more freedom there. The downside is like it has multiple steps, and it's not an end-to-end. These days we're very strongly, there's a big emphasis on that. It does not, and one of the issue there is it's not going to be able to learn low-level interaction. So late fusion means that it's only later stages that I usually will do the later stages. So higher level representation are where I will expect the fusion. And the fusion mechanism could be very simple. It could be just voting, seeing how each of these prediction and vote, you can sum, or you can make it more interesting. And I think that's what I would like to describe over this lecture. Some of the example. One that was in fact very recent, I will describe right now, because I want to look if, let's say that each of these classifier is a neural network. let's suppose that each of these classifiers is a neural network with multiple layers, and I would like to do a late fusion on that. So visually what this could look like, it could be I have one classifier for sentiment based on language, and it could be a multi-layer perceptron. Let's keep it simple for now. And then similarly on acoustic, I have one layer, multiple layer, and then the question is, how do I fuse that? And this was trained maybe with a specific label Y in mind, but let's say this is the last representation. And so, you could just take those two representation and just concatenate. That would be maybe one way, or look at the prediction of one classifier, prediction on the other. But how can I, maybe it would have been better to fuse by taking the intermediate representation. Maybe not just the last representation, but maybe one of the intermediate representation would have been laid. So maybe one of those intermediate would have been, so maybe the last or the second to last will have been the better way to take these two intermediate representation and go to some non-linearity or linearity, and then get my joint representation for them, and then that could be used for prediction. Or it could be that a little bit more complex. It could be that if I take the first of language, because maybe language is in itself maybe already a little bit more high level, because language are words are already segmented, and then so because of that, maybe the representation is a little bit more, let's call it for better word, semantic. So it may make sense that having a earlier representation on the language, while maybe for visual or acoustic, maybe the phenomena that best matches this could be in fact taken later. And that maybe needed to also have at the end, and so maybe in fact it should be at more than one stage. But here, this is done in the, there's no more fine-tuning. The unimodal classifiers are pre-trained, and they're not going to change. They will not change. The question is, how should I, what should be the way of fusing? Where should I get my information to do that final later? And so you can imagine if I have 4 of them fusion here, 4 different layers here, 4 different layers, and let's say that there's more than one way I could fuse them, like different activation function, ReLU or sigmoid. And so the number of combination, 4 times 4 times at least 3, and then that's if that's like for L, and then but if it's L equal 2, it's 4 times 4 times 2 times exponent of 2. So the number of combination, and if we think there's like maybe 3 of these different ways, it gets really large very quickly. This computation gets really, and so there's this new-ish, let's call it new-ish, in the world of neural network and AI, something from 2019 is sometimes seen as an old paper. So let's call it a new-ish paper. It's very interesting. In fact, there's a line of research. This is one of the papers. There are 2 or 3 papers before that, building to that eventually this multimodal fusion architecture. But the idea here is that I would like to try all of them. I would like to try all of these different ways I could fuse this, but this is not feasible. So what will I do? What I do is the following: is I will try the level 1. Level 1 is easier, although there's quite a few. It's like there's 4 of them layers here. There's 4 layers here. So there's 16 different ways I can connect to the modality 1, modality X, and modality Y. There's 16 of them. And that's if I only have one layer of fusion. And so if I L equal 1, I can try all of them. And then for all of the other one where complexity gets can get very large, what is really interesting is I will train and keep updating a surrogate function. And the surrogate function here, what they do is predicting how well the next architecture of the next level will be, what will be the performance. So for example, because level 1, I tried all possible combination, I know that putting this one with this one was relatively a good thing. Although I ended up picking this one as the best one because that was the best out of it. This one and this one was still relatively good. And so what I do is I use this knowledge that I got in level 1 to start predicting of all the combination in level 2. I try to start predicting which of them are likely to have higher accuracy. And that's what this surrogate function is going to be. Is you start predicting for unseen architecture. And then when I get level 2 and I say, hey, I'm going to, there's all the different architecture I could try. And I use this surrogate function for level 1 and say, which of them is likely to give me best accuracy? And I'm going to use a subset of that. And you could add noise to it just in case I got it wrong and I'm overconfident. And then I will take a subset. Maybe there were 100 I'd end up picking 10 of them. And then I will see the accuracy that I got. And then looking at that and seeing the error I made, then I can propagate that error and use that in the surrogate. So I can update my surrogate function so that for level 3, I will not only base my different accuracy, the different accuracy for the different architectures based only on level 1, but I also are going to add whatever I learned from level 2, and I go on and on for that. And so the basic building block is that at the end of the day, I'm going to have, if it's a level 1, it means there's only one fusion unit. There's only one fusion unit. If it's L2, it means there's 2 fusion units. And if it's L3, it means there's 3 fusion in it. A fusion unit will be taking one of these layer and one of these intermediate representation, and then and also whatever from the previous unit. And so there's the one of this, and there's there's 3 hyperparameter. Is one which of these index of the different intermediate representation, which of the index of the intermediate representation, and also how internally I'm pooling them. And I could have simple pooling, or I could have some kind of activation function on top of that. So this is nice. I personally like this idea. And that's what's nice with this is it brings almost a level of interpretability, because then I will know what as interpretable as these intermediate representation is, but at least I will know, is the early fusion, the early representation more important than the late? That allows me to study that. And this was done for audio-visual MNIST. So you have the audio, spoken audio of the digits. You have the visual spoken, and then you bring them together, and you want to predict which digit was spoken. That was the example there. And so, so this is one approach. This is also this. In this case, the choice that the model had to do is it had to, during training, find also which layer of the neural network is the most relevant to this fusion task. But there's also this over, there's a similar idea, although implemented slightly different, is over temporal. You could do the same. You could say, hey, I will predict, my goal is to predict, let's say, emotion. And so I could use acoustic and have maybe an LSTM or some temporal model just for acoustic, and then I train a temporal model for visual, and I train one for language. And there, the question will be not as much like on the layers, but more on those temporal slices. How should I fuse the information, and which one? Because maybe the language at time t and will be related to the visual at time t. And so the idea here is, can I use, and there in that exact model, it's not done through this architecture search, although it will be an interesting extension. I personally, I've only seen often these architecture search done on the layers, but maybe you could also do that architecture search on the temporal. Usually when it's temporal, then people will use more of an attention-based model. So the attention-based model in this case, what it will do is identify within a time slice, identify local evidence. It's kind of a local fusion, and that's why I want to emphasize the concept. Sometimes when you think of fusion, there's the overarching fusion of everything, but here it's a local fusion. It's the idea that you're aggregating together all of these evidence from local multimodal observation. And then you can use that to finally update some kind of more longer term. And so if you believe in a recurrent neural network, it could be through a recurrent neural network, or it could be through some almost more static in the sense that it's still dynamic and changing over time, but you have this unique memory that will get updated. And so, and one example of this, sometimes I say a memory-based fusion is the idea of you're listening to this lecture for the last 30 minutes and then asking yourself, like, what did I remember the most from that last 30 minutes? And how can you make a computational model that like reflect this aspect of listening to a lecture? You listen to a lecture and then suddenly you hear something of, oh, that's interesting. And so it's interesting because there was a nice visual image. There was a good intuition I gave these two together. That was a local fusion. And then you use that and then you accumulate those evidences to finally at the end of the lecture to accumulate all those evidence and have a better understanding of multimodal. And so that's the idea of multimodal fusion. And this one will be able to learn end to end. But this concept of local fusion, I'd like to go more and revisit some of the models that are very popular these days and kind of pinpoint where this local fusion or similarity is very key. And so we're looking at fusion and also looking at kernel function, specifically looking at them as similarity function. And so I'd like to revisit very popular the attention, self-attention models, the transformer and the bird being examples of these self-attention model, and revisit them and find where in this the local fusion is happening. Where is it happening, this local fusion? And so if you remember, the idea of the self-attention was that I have a sequence of observation or a set of observation. And for this set of observation or sequence of observation, I want to contextualize this set of attention with the other one. And so if you remember, the word do by itself is important, but the do and the not really changes the meaning. And so we use the self-attention to be able to find a way to contextualize, to not only say, hey, I have do, my representation do, but I want to learn a new embedding of my word do that takes into consideration the other words. And the other words will be how related. And so for this, I will multiply the x for H2. I will multiply all of these alpha. Alpha are like, how important for this for this x2, how important is the I, how related is the word I, how relevant is the word not, how relevant is the word like, and how relevant is the word it for a better representation of H. That's what this alpha here, these alpha, there are for this H1. And like for this, like how for the word I, new embedding, how relevant is the do and the not and the like and not. So that's the self-attention. This is just a recap of it. And if you remember, how do we get these alpha? How do we compute these alpha? We have those three concepts of like key, query, and values, but I personally think the most important are the key and the query. The key and the query, the key says, hey, this is my current word, like I, and I want to see how is it relevant, the I, how is it relevant to the do, the not, the like, and this. And so I will find, I have my query for I, and I will look at all of these potential matches. That's the key, W key, like the keys. They're all potential matches. And I'm going to find which one has the good match. And a good match is a way of looking at it as a similarity or a local fusion. And so these local match, we're going to look at how well the query, the word I, can match with do or can match with not and like. And right now in the basic transformer, a good match between my key and my query is just a simple dot product of the projection. It's a scalar version. Is I have my original query, I embed it in a linear embedding in this case. I'm embedded, and I take my key, all the possible keys I have, I also embed them, and I just do a dot product to see how similar they are. And that works okay if I have my key and my query the same modality, they're the same granularity, they're the same. But if I have multimodal information, that similarity may not be, I can be hopeful that this linear embedding will be sufficient to handle that difference in modalities and difference with heterogeneous data, but maybe not. And that's why it's healthy when we look at this similar function to maybe start looking at other way to do similar function. And that's why I'd like to talk for a little bit about kernel